Okay, so yesterday we took some time to fill out Pascal's triangle. Can you guys tell me some patterns that you noticed in Pascal's triangle? Was Mr. Ford in there? Yeah. Okay. Some of these are going to fill up in a second, so, okay. Patterns in Pascal's triangle, anyone? How did you fill it out? Caitlin?
So the top, it's kind of like a triangle with the top two numbers make the number below it. So like 1 plus 1 is 2, and 2 plus 1 is 3.
Okay. So we're noticing that each of the boxes add up to the box below that. So that is a great pattern. Did anybody find any other patterns that they use to kind of fill in some of these essay?
The like outer rows, they went one, they just have G ones.
Yep.
And the row after that it comes up by 1.
Okay, so all of the outer rows, you could have filled those in really quick. They're all ones. And then essay just said that the inner diagonal, so the second diagonal in, actually goes up by counting numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Okay, so same thing over here. You should have also noticed that your triangle is symmetrical, right? The left side and the right side are mirrored versions of one another. And so on, and so on. Any other patterns that you guys noticed? Nicole?
I guess third column goes up by 1 piece of increment, so 1 plus 2 is 3.
Okay, so this third diagonal actually goes up, it adds one more each time. So this is like 1 plus 2 equals 3, 3 plus 3 equals 6, 6 plus 4, and then the next one would be add 5, and then we add 6, then we add 7, and then we add 8, and so on. So that was on both of these diagonals as well. But the main pattern that we were looking at is, of course, adding the 2 above to get the 1 below. So if you've exhausted some of those options, you can always just add to get the next, oh sorry, that's 35, not 25, to get the next thing. So I'm not going to fill this all out. We filled up to the 15th row or something like that. I'm just going to fill up to the 8th row here. So here we're getting 56, and then 70, and 56. Okay, so for the purposes of our lesson today, we're just going to look at kind of like the top all the way up to that row with the number 8 in it, and then we'll do some work with those. Okay? All right, so I also asked you to kind of take a look at potentially expanding some of these binomials, some of you guys that got finished early. But if you didn't, we'll do it together now. So we're going to work on just essentially using FOIL and distributive property to see what we get from these various expansions. So anything to the exponent 0 is 1. Yep. Anything to the exponent 1 is itself, yeah. So we get back from this one just a plus b. How do I expand a plus b squared? Kendall? Great, thank you. I'll keep the paper too. Thanks, okay. A plus b times a plus b. So this is not a squared plus b squared, right? That's a big math crime right there. We want to actually FOIL the expression times itself. So we'll do a times a, and then a times b, and then b times a, and b times b. So here, when we expand out, we get a squared, and then a times b is just ab. B times a, we'll keep that in alphabetical order. We'll write it as ab. And then b times b is b squared. So when I simplify here, I get a squared plus, I have 2 ab's plus b squared. What's that? Okay. And then ab cubed, we could write this as a plus b times a plus b times a plus b, or we could write it as a plus b times a plus b squared, because we've already done that part. Okay, so there's no need for me to do more work than I need to. I'm just doing AB times what I just did above, so AB squared. Okay, so we're going to take one more time and use distributive property on this and see what we get when we do each thing in the first bracket times each thing in the second bracket. So I will start by doing a times each of these things. So a times a squared gives me a cubed, and then a times 2ab gives me, no equal sign, thanks. Thank you. Gives me 2a squared b. And then a times b squared gives me ab squared. Okay, just for our mathematical purposes and just so we can see proper like terms, keep everything in alphabetical order, so the a's before the b's. And then we'll do b times a squared. That will give me a squared b. And then b times 2ab gives me 2ab squared. And then b times b squared gives me b cubed. Okay, gather up your like terms. So I have 2ab, or a squared b, plus another a squared b. That gives me 3 of them. And then I also have 1 ab squareds and 2 ab squareds here. That gives me 3 ab squareds. Okay, and then I just have that b cubed there. All right, so I want to observe some of the patterns that we see here and see if we can extend this to the last one over here, a plus b to the exponent 4, without having to use distributive property again here. So there's a couple desks that have opened up over there if anyone wants to grab their own desk. So what do you notice about the pattern on the exponents here? Does anyone notice any kind of patterns that are happening in our expansions? This one's probably the easiest one to look at and see a pattern. Essay?
When you go from left to right, the A's like gets lower.
Okay. Okay. So if we go from left to right, you'll notice we start with the left thing here with the exponent we're expanding by, and we go 3, and then 2, and then 1. That's a great observation. Thank you. And we also notice that if we start with the left thing on, or sorry, the right thing on the right side here with the exponent 3, we count down from there. So it goes 3, and then on the next beat it goes 2, and then on the next beat it goes 1. So we're actually counting down from both sides. We start on the left with the left thing in the bracket. That's why we start with A on the left here. And then for the right side, we start with the thing on the right side of the bracket and start and count down from there. Okay, how about the coefficients? Does anyone notice anything about the coefficients? Let's just go through and take a look at our coefficients here. So I have, for my first expansion, 1. What are the coefficients of these two? Okay, so 1, 1. Okay, what are the coefficients of each term here? 1, 2, 1. Okay, and then the last one? 1, 3, 3, 1. Anyone notice anything? So 1. Thank you. I'll take your paper too. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Pretty cool, right? So that actually gives me these coefficients of each of the expansions here. So 1, 1, 1, 1, 2, 1, and 1, 3, 3, 1. These are actually the horizontal rows of Pascal's triangle. So I think we should be able to kind of use this pattern to do the next one, which is to the exponent 4. So I'm actually going to use the next row down. It will be this one as my coefficients. So maybe we can just write those out and write them out nice and spaced out on my next expansion. 1, 4, 6, 4, 1, taking from that next row on Pascal's triangle. Okay, and then I'm going to start with the value on the left, and I'll start with the exponent that we're expanding by. So it will go a to the 4, and then I'm going to count down as I move to the right. So a to the 4, a to the 3, a squared, a to the 1, and technically we do a to the 0 here, but we know anything to the 0 is just itself, so we don't really need to do a to the 0, and I don't really need to put the 1 here either because a to the 1 is just a, so usually we'll just write it as a. Okay, and then I will start with a thing on the right, again, starting with exponent that is being expanded by, and counting down toward the left. So b4, b to the 3, b squared, and b to the exponent 1. Now these are all separate terms, so they should be separated by some signs in here, so some addition signs. And then when we just simplify this, I'll just remove, I don't need 1 in front of there, so I'll just remove those coefficients of 1. And that's our expansion. Much quicker than doing distributive property with 4 brackets, I think, right? Okay, what do you guys also notice about the exponent values in each of these expressions? Each of these individual terms? Does anyone notice anything? Alex? They all add up to 4. They total 4. So I have 4, and then I have 3 and 1, which makes 4, and then I have 2 and 2, which makes 4, and then I have 1 and 3, which makes 4, and then I have 4. So we get 4s on all of them. And so it will add up all of the exponents on there. Before you do like any exponent laws or anything like that, like if the expression is more complex, the exponents that you initially expand by will all add up to 4. There'll be combinations that add to 4. Okay, so the relation between our Pascal's triangle and the expansion of our binomials. Can somebody tell me what that connection that we found is, just in English? No, did you say? So what did we find out? How did we use Pascal's triangle to expand this? Nicole?
The coefficients match up with the rows like Pascal's triangle.
Great. So the coefficients in a binomial expansion are related to the horizontal rows in Pascal's triangle.
How do we know which row to use?
So we will always use, you'll actually notice that, you know how you told me about those counting numbers? We'll actually use the counting number row to determine which one I want to use. So for instance, like this one, the counting number is 4 in this row, and I'm expanding to the exponent 4. So just look for that value in your row that you're expanding by. If I had an exponent 5, I would use this row, and I'd be using that as an indicator telling me like which one to use. That's okay. I also just like to, Pascal's triangle. I also sometimes just like to consider this, like I'll start with row 0, and that will be the row that I'll use to expand anything to the exponent 0. And then this will be row 1, row 2, row 3, row 4, row 5, and so on. So you'll notice that it corresponds to the counting number row that I'm looking at. Okay? So that's kind of what I usually like to do. Technically, if you want to start with the top one as row 1, it's going to be the one that's, like it'll be n minus 1 as the row that you use there. So you'll take your exponent and use like the next row up from that, or the next row down from that, I should say. Okay? All right, so we're going to try something a little bit more complex than a plus b. So if I'm doing the expansion to the value 3 here, yeah, Joey?
Just go back. Yeah, just didn't get the last part of that.
Yep. So on your test, usually what I do is I will give you something similar to what you had at the beginning of this lesson, where it was some of it's filled out and some of it's blank, and you might fill in a couple of the values there. As long as you know that the 2 above add to the 1 below, you should be fine to enter it all in, and then you'll use that for the rest of your stuff. Marianne?
Will we ever do like the entire like bottom row for
Well, I mean, technically Pascal's triangle actually continues forever. Like I ended yours at 15 here, but it actually goes forever. So,
Like the entirety of the one that you give us?
no, no. We're only going to do like basic expansions. Okay, so here we're going to expand to the exponent 3. So what should my coefficients be? Like which part of Pascal's triangle am I using here? Let's look back. Just going to erase all of this. 1, 3, 3, 1, that's right. Sorry, I actually just wanted to keep that part. 4, 1, 1. So we're going to use the row with the counting number 3 in it. So I'll use 1, 3, 3, 1, and that should be a 5. And we will start just by writing those out nice and spaced out here. So 1, 3, 3, 1. And then I'm going to go to the thing on the left of my binomial, which is 2x. And I will start with cubed on the left. So I always start with the value of the exponent that I'm expanding with. And then I'll count down toward the right from there. So it'll be 3, 2, 1, and then technically 2x to the 0. That just gives us back 1. So we don't really need to write that one. Okay, and then I'll start with the thing on the right-hand side here. So, and starting with the exponent I'm expanding by, and I will count. So 3, 2, 1, and then I separate them all out with signs here. Okay, I do need to take a couple extra steps here and actually simplify this expression. So if I happen to have like something that's being cubed, I actually want to calculate that, like I want to figure out what that is cubed, and I'm going to expand and simplify here essentially. So we're going to follow BEDMAS when we're expanding, and we're going to make sure that we do exponents first, and then any multiplications that we have, and then if we happen to have any like terms, we can add those together. Okay? So 2x cubed. How do I do 2x cubed? Bonnie? We cube the 2, and we also cube the x. So 2 cubed is 8, and x cubed is obviously just x cubed. Good. Okay. The 3 here is just going to hang out for a second. 2x squared, that's like 2x times 2x. We'll get 4x squared. So I actually have to make sure I square each component in here, right? I square the coefficient, and I square the variable. And then y to the 1 can just be y. And then we know, of course, 2x to the exponent 1 is just 2x. And 1y cubed, we'll just write that as y cubed. We don't ever really write the coefficient of 1 in front of anything. Okay, and then the last thing I want to do is I want to make sure all coefficients, because things like this are all being multiplied together, I want to make sure all the coefficients get multiplied and just put in front of the variables. Okay, so for this next one here, I'm going to do 3 times 4 to get 12. And then for this next one, I want to do 3 times 2 to get 6. And then the last step that I'm going to take is I'm just going to make sure that there aren't any like terms that need to be put together. So are there any like terms in this expression that I need to add? Natalie says no. Why no, Natalie? Right, so I have to have the same variable and also the same exponent combination on those variables. So here I have an x squared y, but here I have an xy squared. So those are actually 2 different terms. I can't add those things together. So this is actually my final answer here. There's no Kleenex. Sorry. Do you want to go in and grab one from the office?
Yeah.
Okay.
I'm gonna die of
Okay. Questions? Is anyone confused as to how did you get from this to this? Let me know. We're okay? Okay. Save yourself a little bit of space here. Try not to write too big. This one's going to be a little bit more complicated. We're going to expand to the exponent 5, so we're going to have quite a few terms. Which row do I want to use? What row makes up my coefficients when I'm expanding to the exponent 5? Joey?
5.
Okay, so which one is that here? What are the coefficients?
Sorry?
What are the coefficients then of my expansion?
1, 5, 10, 10, 5.
Right, 1, 5, 10, 10, 5, 1. So that's what we're going to start by writing out, nice and spaced out. Leave yourself some space here. I'm actually even going to zoom in a little bit here so I have a wider space. Okay, so 1, 5, 10, 10, 5, and 1. All right, we're going to start with the thing on the left with the exponent 5 and count our way down toward the right. So 2x to the 5, 2x to the 4, 2x cubed, 2x squared. Oh, that was weird. And 2x to the exponent 1. Thank you. Okay, and then we're going to start with the thing on the right and start on the right with 5, 4, 3, 2, 1, and so on. I might need a little, tiny bit more space over here. Okay, so 3y squared all to the exponent 5, and then 3y squared all to the exponent 4. 3y squared all to the exponent 3, and then just continuing to count down here, we'll get 2 and 1. Okay, and separate all your terms with plus signs.
Will they ever be minus?
So if your second term is a minus, what I would do, so if it were something like this, let's say, I would actually rephrase this as plus negative 3y squared, and then for each of these you'd be putting in a negative 3y squared to your various exponents. So some of them will become negatives and some of them will become positives, but you're still going to put pluses in between all your terms, and then you'll see which ones become positive and negative. Good question. Okay, so I'm going to take this term by term here. We're going to take it slow. Please stop me at any point if you are confused as to where certain terms came from. Okay, so let's start with this one. I want to do 2 to the 5 and also x to the 5. So what's 2 to the exponent 5? 32. So this one will be 32x to the 5. Okay, next term, we might have to do a couple simplifications here, which is okay. Next term, I'm going to let the 5 hang out here for a couple seconds. I want to do 2 to the 4 and x to the 4. So 2 to the 4 is 16, and the x will just have that exponent of 4. 3y squared to the exponent 1 just gives me back itself, so it'll be 3y squared. Okay, next term, do this one in purple. 10's going to hang out for a couple minutes here, and I want to do 2 cubed and x cubed. That gives me 8x cubed. And then I want to do 3 squared and y squared squared. What happens when I do an exponent of an exponent? What do I do with those? Bonnie? You multiply them. Okay, so here I'll get 3 squared, which is 9. And y squared squared, I take the squared squared, the 2's, and I multiply them together, and we get 4. Okay, so just be mindful of that. Okay, so 2 squared and x squared gives me 4x squared. And then 3 cubed and y squared cubed. So 3 cubed, correct me if I'm wrong, 27. And then y squared cubed. What's y squared cubed? Y to the 6, yes, because we multiply together when we have an exponent of an exponent. Okay, and then just finishing up here, taking care of all of our exponent rules first, we are going to do 2x to the 1 is just simply 2x, and then we'll do 3 to the exponent 4 and y squared to the exponent 4. What's 3 to the 4? Three to the exponent 4, anybody? 81, yes, very good. And then y to what exponent? yes, 2 times 4. Okay, last one. We'll do this one in black. 3 to the 5, 243. And y squared to the 5 is y to the exponent 10. 243 is correct, right? Yeah. Okay, so we're following BEDMAS here. We're making sure that we do exponents first. And then in all of these terms, I just want to look through and make sure all the coefficients are just multiplied together and expressed as a single coefficient at the front of that term. So this one can stay. This one is fully simplified. Actually, sorry, I'm just going to make my pen a little bit thinner here. Okay, so 32 can stay. That's all simplified. With this one, I need to take all my coefficients and just multiply them together as a single coefficient. So I need to do 5 times 16 times 3. Can someone do that for us? 240? Great. Everyone else get that? I'll take your silence as a yes, meaning you're all using your calculators right now, of course. Okay, and then I want 10 times 8 times 9. That gives us 720. Okay, and then I want 10 times 4 times 27 for this next term.
Is there not one x3?
Oh yeah, thank you. Great, thanks. 4 times 10 times 27, Bonnie? Great, 1080, x squared, y to the exponent 6. 5 times 2 times 81, that's 810. xy to the 8, and then the last term is already simplified. It's just 243, and then times y to the exponent 10. Great. Any like terms that need to be gathered? Do we have any additions that need to be done? I think these are all different terms because although they share some similar variables, the variables have different exponents. So this is our final answer. Okay? You can imagine how much longer this would take if we were trying to do this with distributive property, right? So Pascal's triangle has actually just, I know this was long to begin with, but if we were trying to do this to the exponent 5 and actually FOIL everything, it would have taken a really long time. So we did save ourselves quite a bit of time by using Pascal's triangle. So I do want you guys to notice a couple things. The first thing is we talked about how the exponents will all add to this expansion exponent value. That's not true if you're doing exponent of an exponent once you get to your final answer. But in your initial exponent, you should notice that you have 5, 4 and 1, 3 and 2, 2 and 3, 1 and 4, and 5. That doesn't stay for our final answer because we had an exponent in our binomial. So when we did an exponent of an exponent, they weren't all adding to 5 once we got to our final answer. But your initial expansion, the two combinations should all add to that value. Also, I want you guys to notice in all of our expansions that we've done so far, how many terms did we end up with when compared to our exponent value? So here we were expanding by exponent 5. How many terms did we get in our expansion? 6. Here we were expanding by exponent 3. How many terms did we get? 4. Here we were expanding by the exponent 4. How many total terms did we get? 5. So can you guys tell me if I expand to the exponent 20, how many terms I would expect to get in my expansion? 21 terms. Okay, so it's one more term than the exponent value. And this is in the initial expansion. If you happened to have something like x plus 2x squared to the exponent 20, your initial expansion would give you 21 terms, but you might find that you have some common terms at the end that have to be added. So this is basically just telling you the initial expansion will give you 21 terms. That doesn't necessarily mean that once you expand and simplify, you will always have 21 terms. It's just that initial expansion. Okay? If I see that these terms don't have any common variables, then I won't be able to add any like terms at the end anyways. So when I have x and a y, I know for sure that there'll be 21 terms and I won't be able to add any of them at the end. Okay? Do we need a little mental break before we finish the last few? Okay. Short break and then we will finish up. Okay, so for the rest of our lesson, we're just going to kind of do a couple different types of questions that involve pinpointing a specific term or coefficient in our expansion. So the nice thing about these is that we don't have to do the entire expansion. We're just going to do some like counting, and we'll use our rows of Pascal's triangle. So for this one here, I'm expanding to the exponent 7. So I'm going to look over here at the row with the counting number 7. And if you want, you can write out just like all of the coefficients, but we're just going to focus in on one because I'm interested in just the second term. But these are, if we were doing the whole expansion, those are the terms or the values of the coefficients that we'd be focusing in on. Yep.
Are we not doing example 3?
Oh, did I miss example 3? We did example 3. It's 21 terms.
Oh,
Okay, so if I'm just focusing in on the second term here, Emmanuel, put your phone away. Joey, can you shut the back door as well? It's just a little loud. I'm going to start with the term on the left with the exponent 7. And I don't have to go very far because I'm just focusing in on the second term here. So if I do 7 and then 6, I've got my value, and I'm pretty much done there for that one. What do I know about this term's exponent value at this location?
1.
Why is it 1, Katie?
Because it's the last one before
Yes, and also what do we know about these two values?
it equals
They have to add to 7, right? So as soon as I know one of them, I know the other one. Okay, so we're just going to focus in on simplifying this term here. It's going to be 7 times 6 to give me 42x to the exponent 6. That is the second term of our expansion. That's all we're asked about, right? Okay, fifth term of the expansion. So I'm going to look over again at the fifth row. So looking at eighth row for expansion by exponent 8. So if you want, you can just write out 1, 2, 3, 4, and then 5. I'm actually just going to stop right at 5 there because I don't really need any more than that. And then I'm actually just going to count. So if I start with 3y to the 8 here, it'll be 3y. Everyone just look up here for 1 second as I count because I just don't want you to get lost. So I'm not going to write everything out. I'm just going to count. So it's going to be 3y to the 8, 3y to the 7, 3y to the 6, 3y to the 5, and the term I need, 3y to the 4. Okay? So if you want, of course, you can write out all the terms, but I think we can just count down without having to write the value out every single time. So again, I was starting with 3y to the 8, 3y to the 7, to the 6, to the 5, and then I got to the 4, right? So again, we don't have to write it all out, but you can if you want to. And then what do I know about the term? Oh, so this is actually what essay asked me about earlier. So I would actually rewrite this as this, just so I know that there are some terms that will become positive and some that will become negative. So my second term here is actually going to be -4. And what do I know about the exponent on that -4 if this one is 4 for the 3y? Nicole? Yeah. Why?
Because it has to add up to 8.
These have to add to this value, 8. Good. Okay, so let's simplify this term here.
How do you know it's negative?
Because, well, anytime I have a negative here, I'm going to express it as plus a negative. Just so, because some terms will become negative and some will become positive. So when I do my expansion, I'll put plus signs between all of them, but some will turn positive and some will turn negative depending on what I put this negative to the exponent of. Like in this one, this negative will become positive because it's to an even exponent. But for the other, like for the odd ones, the negative will remain for those terms. Kylie? You can write it, thank you. You can write it all out if you want, but we don't need to because we're just looking for the 5th term. So I'm just using the other ones to count. Yeah. Okay, so here we're just going to simplify. Use your bedmass and exponent laws. So 3 to the 4 is 81. And negative 4 to the 4, what do we get there? Thank you. Negative 4 to the exponent 4. What'd you get?
Oh, wait.
Nicole? 256. Very good. And now we just need to simplify all these coefficients. So 70 times 81 times 256. What'd you get, Kaylin? It's a big number. Just read out the numbers then.
14515.
Great. So that's 1,451,520. Sweet. Definitely don't want to do that expansion. That would be a big one. Questions for this? So just for these ones, we don't have to write everything out. We're just focusing in on that one term. And if you want to write your coefficients just as placeholders for you to count down so that you can find the correct exponent value, that's great. And then the other type of question that you might approach is this type of question where it just asks for the coefficient of a particular term. So it's asking for the coefficient that falls on the x cubed term. So for this one, because we're expanding to the exponent 6, I'm going to use this row. So 1, 6, 15, 20. This is supposed to be 15. 15, 6, 1. And then I really just want to figure out where the x cubed term is, and as soon as I find that, I can just kind of stop writing things out. So we'll start with x on the left, so it'll be x6, x5, x4. Oh, and this one's the one I need, x cubed. Perfect. As soon as I know that, I know the exponent on my 6 as well. What's the exponent on our 6 there? 3. Okay, good. So in order to find the final coefficient here, I just need to simplify that 6x cubed, or the 6 cubed and the 20. So what's 20 times 6 cubed? 1,000? Okay, 4,320. So the answer to my question, it's asking me for the coefficient. So this is actually the answer to my question. It's 4,320. Great. And then last one, we're going to try it one more time. So same expansion. So I'm going to use the same row for my coefficients. It'll be 1, 6, 15, 20, 15, and then 6 and 1. And then I just want to see where I end up with an x squared and a y to the exponent 4 in the same term. So here I'd be starting with y on the left and counting down. All I need to do is count down to 4. Because as soon as I have that component of my term. So there's my 4 right there. I can just stop. I don't need the rest of this now. And I know that my 3x will have what exponent on it if I know that y has an exponent 4? 2, because they have to add to 6. Okay, so we're just going to simplify. I'm interested in the coefficient that results from this. So this is times 9x squared, and then I just want to do 15 times 9 to get the coefficient value there. So I think we get, correct me if I'm wrong, is it 135? Pretty sure that's right. And then usually we'll just write the variables in alphabetical order. So my answer to this question is 135. Okay? So practice this stuff, okay? Make sure that you kind of know how to use the triangle and work on your, if you can count, you can do this, right? And if you can do exponents and multiplication and stuff, you can do it, okay?